It's always a good thing. So just kind of a couple of review slides. We're going to continue talking about the hydrological cycle or the water cycle. We're going to end up talking about clouds today, I think. I think we'll get that far. But for the water cycle, what's important is to, and I have ice up here, and I have liquid water, and of course I have boiling water. You know, it's important to get a sense for the fact that we know that we can add heat to ice to get it to liquefy. We can add heat to water to get it to vaporize. Now, not so intuitive, and I touched on this on Friday, is this other. The fact that, let's see, make sure I get this right. As a gas, okay, liquefies, that would be this one right here, okay? Actually, energy is released, and as a liquid freezes, energy is also released. Okay, so these are energy released on this side. Okay, and then actually, I thought of you guys this morning when I went out to try to get the frost off of my car. Okay, what is that? That's deposition. Okay, I'll just go ahead and put frost there. Basically, water went straight from being a gas to being a solid. And water was released. If we have a little probe there, temperature probe, we can actually see during the deposition process, it going from a gas to frost, there'd be a little bit of energy released. Some farmers of citrus fruit, that sort of thing, actually will coat their fruit with liquid knowing that it's going to freeze, because when liquid freezes, it releases some heat, and they count on that. Is that not weird or what? So anyway. All right. So let's see, did I do this? I guess I did that one. All right. So let's go on then. So when will water condense? So as I have it up here, I don't know if you guys can see, this is here's my boiling water. And do you see the water up here in the watch glass? Okay, that water is condensed, right? Okay, so I could take that watch glass off, and then the water vapor would go on and do its thing. Can you kind of see the smoke, that sort of thing? Does that kind of look like a cloud? Yep. So anytime that you can see water like that, actually, water is now not a vapor or gas. Water is a liquid. So water is condensed. So anytime we see a white cloud, water is condensed. Yeah, you're like, is that really condensed? Yep, it's condensed. Have you ever exhaled on a cold morning and you see your breath? Okay, in your breath, what you're seeing is your water vapor is actually condensing. Water is, it's a gas here, and we exhale, and usually you don't see it. Okay, but if it's cold enough, basically it would go ahead and condense. Okay, so those are kind of things. So when will water do this? When will water condense? Well, when we talked about these different phases, the solid, the liquid, and the gas, I had a figure that kind of showed that here in its solid state we have a lot of intermolecular bonds. It's all stuck together. Here in its liquid state, a few less intermolecular bonds, still intermolecular bonds. In its gaseous state, no intermolecular bonds. So what has to happen for water to condense, for water to go from a vapor to a liquid, is those intermolecular bonds need to form again. That's exactly what's happening. So how do we get that to happen? How do we get water vapor to go into its liquid state? Well, we're going to see here in meteorology there are actually two major ways of making that happen. One is to bump up the amount of water vapor molecules that are close together. Okay, that's just basically to increase the water vapor molecules. And when you do that, they get closer together. They have more of a chance of basically reaching out and forming those intermolecular bonds to condense. Okay, and we're going to talk more about humidity. So you figure, when is there a lot of water vapor in the air? Well, on these hot summer days, you'd say, man, it's humid out here. And most people are like, I know high humidity means a lot of water vapor, and you're totally right. Okay. The other way we can get them to condense actually kind of goes back to, for instance, on a cold winter day, when you exhale out, okay, when you see your breath, basically you're counting on the cold temperatures, basically slowing down those molecules. One of the things about water in its three different phases is, if I were to ask you, how much kinetic energy does this have? You'd say a lot, right? How much energy does this have? Kinetic energy does liquid water have? Well, a little bit. How much kinetic energy does this ice cube have? Not much. So one of the things is you kind of ramp it down. You're also slowing it down. You're taking its kinetic energy away. So the way we slow it down is to cool it down. Okay, so now the reason, honestly, that we see a condensation on the top of that watch glass is because it's cooler here, appreciably cooler up here than it is down here. So basically that's why we get condensation. Okay, so those two ways. So put it another way, if you're after condensation from water vapor to go ahead and liquefy, you're going to have your best bet high humidity, high water vapor content. We'll have to talk about how do we gauge humidity, and cooler temperatures. Seems reasonable. So one of the things I want to talk about is the whole clouds. Okay, we're going to talk about 10 cloud types, and we're going to talk about why do clouds form. Well, I already told you clouds are basically water vapor that has liquefied. Well, why does it liquefy? Well, these are the two ways. Okay, you can go ahead and have high humidity and or cooler temperatures, and you're going to get condensation. You can get a cloud then. Okay, so I've got 3 chambers kind of from left to right. They start out this way. This chamber is got liquid water on the bottom, okay, and it's got a dry air above it. Sometimes I kind of pretend that must be like a saran wrap or something, kind of separating the liquid water from your dry air chamber. On the top there is something kind of interesting. This actually is a pressure gauge, and that's selective pressure gauge for measuring. I'll put the total KE, kinetic energy, of the water vapor. So actually right now, no water vapor in there, okay? And the pressure gauge is sitting at 0. Well, we go ahead and remove the saran wrap. If you remove the saran wrap, then right away, one of the things maybe intuitively you know is that the drier the air is, basically the more likely, if you have an open pan of water, for instance. I brought this. I got it at Walgreens. My mom got one. I thought it was so cool, so I got me one too. It is a simple humidifier. Now, as we're going into the winter season, everything's dry. Okay, our skin gets dry. Our rooms are dry. This is a little cheap little humidifier. Okay, it's pretty cool. It's pretty cool, I'll warn you. So basically, there's a pan of water there. So I'm supposed to put just like, fill it 3/4 full. And this is just a stone. It's just a rock. Okay, and what happens is the liquid will wick up here. Okay, and then actually this will be little water molecules. Okay, and then it will go ahead and evaporate into the room. Okay, the drier the room, the more that's going to happen. Okay, that is definitely the deal of it. And right now it's humidifying my office these days. Okay, so when we took that saran wrap off, okay, definitely we had evaporation. Okay, but to a certain extent it's going to condense back in, condensation. Okay, evaporation, condensation. Now, the way this is, you see there's definitely more evaporation than condensation. Do you see our pressure gauge going up a little bit? Okay, so the pressure gauge actually is selective for water molecules, and those water vapor molecules are banging against it and making the gauge go up. Okay, so we let it sit there for a while, and then something special is going to happen. Okay, so given enough time, that last one there, can you see how far the pressure gauge is? Okay, so the fact that the pressure gauge is really pegging out there means that I must have a lot of water vapor in that last chamber. So actually that last chamber kind of reminds me of this little scenario up here where we actually see water condensing and falling back down. That last chamber is what we call saturated. Some cool things about saturation is if you were to look at the number of water molecules that are evaporating, I got 5 there. They're equal to the number that are condensing. I got 5 there. Okay, saturation. We definitely still have evaporation, but now we have condensation at the equal rate. Okay, that's what we call saturation or equilibrium. Right then and there, and actually we're going to be talking more about this this is actually a player 100% RH. It's a player in weather. A lot of times you're like, well, I don't know what it's going to do. Is it going to rain? Is it really muggy outside? Are we at 100% relative humidity? Well, if you're at 100% relative humidity, probably so, okay? So high humidity, we said, favors this whole condensation process. So we need to talk about humidity a little bit. And I want to introduce you to two things other than RH stands for relative humidity. And if you're like one of these people that like to look at the weather forecast people, they'll give you RH. They'll give you the relative humidity. And it's a great way. There are a couple of other ways to express how much water vapor there is in the air I want to look at right quick. Okay? So the other two I want to look at are absolute humidity and mixing ratio. And they look a little more scientific than relative humidity. But actually the two I want to look at are related back to relative humidity. So here's what it looks like. I have a couple pictures to go along with these. Okay, so absolute humidity and mixing ratio are both like little fractions. And let's look at those little fractions, what they have in common. Absolute humidity and mixing ratio both have mass of water in the top. Okay, what they differ by is what they have in the bottom. With absolute humidity, you're talking about what's the volume of air. And in mixing ratio, you're talking about what is the kilogram of dry air. So I have a couple examples here. So first off, over here, this scenario is we've got 20 grams of water vapor. 20 grams. That would be the little water vapor scooting around in there. Okay. And we've got the volume is 1 cubic meter. So we can take that 20 grams divided by 1 cubic meter and get absolute humidity. Okay, that's it. So the mass of water vapor divided by the volume. The other one, okay, we take mass of water vapor again and we divide it by what's the mass of dry air. So 20 kilograms divided by 1 kilogram of dry air. One of the things I want to emphasize on this slide is this figure actually has two orbs of air. Watch what happens when I let this air go up. It goes from this volume to this volume. That is an important player. I wouldn't focus too much on the absolute humidity mixing ratio if you don't want to, but look at how it swells. Chunks of air will swell like that when they go up. They just do. Okay. One of the things we maybe can talk about is, do you guys know when you climb a mountain that the air gets thinner? Okay, the air does get thinner, so I've heard. And it's true, as we go up in elevation, air actually is thinner. It's less dense. So this whole going up and swelling is kind of a natural sort of thing of a chunk of air to do. Have you ever seen these weather balloons? That it's amazing that twice a day throughout the world, I want to say, they have these weather stations that release a weather balloon up into the air. And it's got this little box on it that as it rises, it basically sends back data to the people who sent it up. But my point is going to be they start out with a weather balloon that, oh, it's pretty big. But what I've read is that weather balloon will swell too because the pressure is less and less and less. And the thing has latex that will let it get as big as a house. Then, of course, the latex can't keep it anymore and it pops. Okay, and it's got a little parachute on it. The little thing does. It's got a little parachute on it and it falls back to Earth and hopefully they find it again. I want to find one of those one of these days. Okay, so that's kind of the rising and the swelling. In the meantime, we do have water vapor related to different ways of saying humidity. Now, the next slide, I think what I'm going to focus on is this one, mixing ratio. Okay? So here's the deal. Have you ever heard that warm air holds more moisture, water vapor, than cold air? There's a certain truth to that. Warm air, if your air is warm, it can hold more water vapor. And kind of like we said a minute ago, if you take warm air, it's got a certain amount of water vapor, and you cool it down. Well, if you've got high humidity, you take that air and cool it down, you're going to go ahead and it's going to condense. So warm air can hold more water vapor. And actually, this is showing you that. What this is to reach saturation. Now let's kind of get our bearings. What is saturation? Saturation is 100% RH. That's what saturation is. To get to saturation, these are the amounts of water vapor. So this is vapor, water vapor, you need to get to or add in order to reach saturation at these temperatures. Okay, so here we go. We're warming. Let's go from the top bottom. Okay, we're getting warmer and warmer temperatures. What happens to the amount of water vapor it can hold at those temperatures? It increases. That's it. Okay, so these are saturation amounts. And these, you know, if you're a scientist, this is the ones you're kind of looking at. Are we getting close to 100% relative humidity? I've got a few figures coming up, starting with actually something that is at 20 degrees Celsius. So at 20 degrees Celsius, okay, I want you to see what the saturation, or is it 25? I'll better soak both of them now. I think it's 25. At 20 and 25, okay, your saturation amount is 14 grams of water vapor per kilogram of dry air versus 20 grams of water vapor per kilogram of dry air. Okay. So when we calculate the thing that we're used to looking at in the weather report, you know, what is your percent relative humidity? You know, is it humid out there or is it kind of dry out there? What they're doing basically, and we'll be doing this in the lab on Wednesday, is getting a fix of the real water vapor we have in the room, okay, and we do, that's called the AC, the actual humidity, okay, and we divide that by the humidity on this table, okay. So I have some examples coming up. So MC is from this table. That's the maximum humidity you can have at that temperature. All right. So like I said, and like you guys know, if it's pushing 100% relative humidity, you're like, oh, I think it's going to rain. Okay, or I think we're going to have fog, you know, or I think something's going to happen. Frost, dew, 100% relative humidity. So like I said a minute ago, how do you, if your goal is to have water vapor condense, what are your options? Okay, you can either increase how much water vapor you have in there, okay, or you can cool it down, and by cooling it down, your air holds less water vapor at those lower temperatures. Okay, so here's a couple of little things to throw at you. So I'm going to show this same flask in 3 different scenarios, and in each of them, the 25 degrees Celsius is going to be the temperature of kind of our system. So 25 degrees Celsius, a few slides ago, that corresponds to a saturation mixing ratio of 20 grams. So that 20 grams came from the table. Okay, so that's from the table. In this particular scenario, they're saying, oh, we've got 5 grams of water vapor running around in there. We've got 5 grams. That's cool. They went ahead, conveniently said the amount of dry air is 1 kilogram. So here's the deal. This is what we have. So that's our actual AC. Okay. And this is actually from the table. That is our MC, our maximum amount. So that's why down here to say, well, kind of relatively speaking to maxing out, what is our relative humidity? So it's actual divided by the maximum. So it's 5 divided by 20. So we're at 25% relative humidity. So just like that scenario a minute ago with the saran wrap over the chamber, okay, dividing the liquid water from the dry air in the chamber above it, okay. Just like that, we go ahead and there's more water going to evaporate. So you give it a little bit of time and your chamber's not going to be so dry. So instead of 5, we've got 10, same temperature. So now we have 10 divided by 20. So we're at 50% relative humidity. So you know what's going to happen. It's going to actually kind of reach what we call saturation or equilibration. So given enough time at that same temperature, Now finally we have saturation here. This is the water is saturated, or excuse me, the air is saturated. Okay, we know that because you're at 100% relative humidity, and we also know that because you're at 20 grams of water, and that's how much water it can hold at that temperature. Very good. Well, this is a little different scenario. Again, I've got 3 flasks here I'm going to show you, but in this case, I'm going to vary the temperature. So on the table a little bit ago, okay, if you look at 20 degrees Celsius, the table says the maximum amount of water vapor that 1 kilogram of dry air can hold is 14. So that came from the table. In this particular scenario, I'm at 7 grams of water. Okay, so if you divide 7 by 14, you're at 50% relative humidity. Well, I'm going to jack up the temperature, or I'm going to cool down the temperature, sorry. So if you look at that table, you'll notice that at 10 degrees Celsius, a 1 kilogram of dry air can hold 7 grams of water vapor. So I'm going to leave my water vapor at 7 grams, and oh my gosh, so I've got 7 and 7. So I'm at 100% saturation here. You would expect to see some sort of condensation. So the last scenario actually is to cool it further. And so, not so surprising, the maximum amount of water vapor that can be held for 1 kilogram of dry air at 0 degrees Celsius is 3.5 grams, okay? So here I am, and notice that I didn't, let's see, how do I say this? I didn't take 7 divided by 3.5, because that would have given me over 100% relative humidity. Instead, what your author's done, or what this author's done, is basically said you had 3.5 grams of water basically come out of being a vapor and being a puddle of liquid there. And you ended up still keeping 3.5 grams of water vapor. I buy that. So there are 2, like if you're a weather junkie, okay, not only do you see the relative humidity, okay, what's the humidity like? Probably see the barometric pressure, we're going to be talking about that later too. But you see the real temperature, and I brought some thermometer probes here, I'm not sure if we're going to use them, but you see the real temperature, okay, that's what your weather report will say. But it also gives you a feels like temperature. There's 2 feels like temperatures. We're going to start out with the hot feels like temperature, and then we're going to actually do the cold feels like temperature when we talk about wind. So the hot feels like temperature looks like this. Basically, it says that, and I don't know if you can see this very good. If you're running, let's see, let's pick something oppressive. Let's say you're running at 90% relative humidity. You're like, dang, it's a hot summer day. And you're running at 94 degrees Fahrenheit. That's what this says, okay? Your feels like temperature is actually 131 Fahrenheit. Like, oh, I didn't need to hear that, okay? The thing about humidity, okay, your humidity makes you feel like crap, okay? If we were to go ahead and go to Arizona where they say it's a dry heat, right? Let's jack that down to 40% relative humidity at that same 94 degrees Fahrenheit. 40% relative humidity at 94 degrees. Okay, you're still pretty hot. Instead of being like 94, you're like at 97. So the thing with increasing relative humidity is it makes us feel hotter. Okay, and why is that? I'm going to kind of talk you through why that is. Why does increased relative humidity make us feel like crap? Okay, well, in a nutshell, and I'm going to talk you through why our bodies respond this way, and it kind of goes back to my mom's little globe thing. Oh, this feels cool. This is cool. What? You guys kind of feel that little orb. Cool. It is cold. Feel the orb. Is it cold? Okay. So here's the deal: is evaporation, which is it's really want to do that. I mean, because the air is pretty dry, it wants to evaporate. Okay. But evaporation requires energy. Yeah, I know. Evaporation requires energy. So actually, as it evaporates, which it's really glad to do, it's actually robbing some thermal energy of the air around it. So it's actually, when water goes from a liquid to a gas, it basically cools down. It's a cooling effect of water doing that. So anyway, why do we feel so bad when it's high humidity? Well, I'll put it like this, what I started saying, is if I were to go to try to use this humidifier in the summertime, aren't your houses kind of all, we use dehumidifiers in the summertime, don't we? If I were to try to do this in the summertime when it was already very humid, okay, this would not work. It'd be like, you know what? You already have all that water vapor in the air. I'm not going to be in a hurry to go ahead and go from a liquid to a gas. I'm just not, okay? So the thing is when we're outside and you're at like, what did I say, 90% relative humidity, you know, water just does not evaporate. And so the reason that makes us feel like crap is a cooling mechanism that we have developed is that sweat. Okay, our bodies count on sweating. Actually, biologically speaking, our sweat serves a purpose. Not only does it look cool, like, hey, I worked out, right? But your sweat also serves a purpose because that liquid water on our skin, okay, we're counting on it just like what this did, okay? We're counting on basically that liquid going to a vapor and in the meantime having a cooling effect. It really does. It cools us off when our sweat evaporates. So now here's the problem. When it's already high humidity and our sweat tries to evaporate, you're like, I don't think so. You can keep your liquids in sweat, okay? So under high humid conditions, that cooling mechanism does not work. That's it. That's why we feel so bad. So again, there's two feels-like temperatures. And in the summertime, it's going to be what we call the heat index, which basically factors relative humidity in with what our thermometer reads. Okay, now our real thermometer, this is the real deal, what our thermometer reads, and the feels like temperature just kind of adds a little bit to what our body do. The other one I want to talk about is the wind chill effect, and that's also a feels like temperature coming up. All right. So, clouds. So, clouds are beautiful, milky white, because I want you to just get out of this class, because basically water has condensed, water has liquefied. Now, you might be like me, like, it's clouds are milky white because basically water vapor has gone to be a liquid, but you're like, liquid water, we don't. It's like transparent. So why do we see a cloud? Well, this might help. It may or may not. Okay. This actually is called cool down. I don't know. And you pump it up, okay, and basically it just, it won't blow, I promise. It creates a pressure in here, and then actually, see that little white valve? Okay, that will go ahead and open that pressure. Now, the other thing is I have liquid water in here. That's just liquid water. Okay. So my point was going to be, let's see if we can see this liquid water. Can you see it? Yeah, it's not opaque.
Okay, I see it.
Okay, and so picture that, like those little droplets of water. Picture that being like your cloud. It's kind of followed, right?
It's an umbrella.
Yeah. The other thing is actually, as I'm standing here, the chopping water up into tiny little pieces like this, okay, makes it want to evaporate more. And again, when the water evaporates, goes from a liquid to a gas, that's when you get your cooling effect. So that's why this works as a nice cooling. Good. All right. So hopefully you're convinced. So to get a cloud to form, we can actually, to get water to go from its vapor to its liquid, we can either increase the humidity, but more than likely what we're going to do is cool the temperature. So basically we're going to take water vapor and we're going to cool it down to get liquid. Okay? So the best way for clouds is to basically, and I remember I told you to focus on kind of the expanding chunk of air a little bit ago. If you take a chunk of air and let it go up, it's going to get bigger. And as it gets bigger, actually, that's what we say work. It's doing work. Okay? And as it does work, actually, it's going to cool down. So that's kind of what we have with kind of getting a chunk of air to cool down. You just have to get it to rise and it will get bigger. So how do we get a chunk of air to rise? And actually, there's 4 ways you can get a chunk of air to rise. One is mountains. Okay? One of the things, and we'll talk more about this later in this class, but if you were just to look at a weather map, okay, this is your big weather map of North America, and if I were to ask you which side are you going to look on the east, or are you going to look on the west to see where our weather is going to come from, you're probably going to say the west, okay, and you're right, okay. Basically, we have what we call a prevailing wind that comes from our west, and we'll talk more about that too. So just picture that prevailing wind taking a chunk of air off the Pacific Ocean and slamming it up against the Rockies, okay? So that chunk of air is going to go up and over, okay? That's called actually orographic lifting. One way to get mountains, okay? There's one way to get mountains. One way to get clouds. Get that chunk of air rising, it cools down. How else can we get chunks of air rising? Oh my gosh, did you guys hear Wednesday that we're actually in store for some interesting weather, maybe thunderstorms, that sort of thing? If your dogs are like mine, they're not looking forward to it, right? They don't like the boomers. But here in the Midwest, we don't have mountains, but we definitely have chunks of air rising. We have our fair share of clouds and that sort of thing. What is a thunderstorm? Basically, a thunderstorm is a cloud it's a cloud on steroids rising, okay? That's what thunderstorms are. So what we're going to have coming in on Wednesday is what we call a cold front. So a chunk of air that's cold and a chunk of air that's warm. Okay, the chunk of air that's cold actually hugs the ground, and it basically runs into that warm air, lifts it up, and that warm air is probably moist, and it creates our thunderstorms. That's it. Okay, so chunks of air that rise can go ahead and condense and create clouds. So that's one way. We call that frontal lifting. How else can you get a chunk of air rising? This is kind of an innocent sort of chunk of air rising. A lot of times in the summertime we'll kind of have these like little clouds that appear late in the afternoon, then they'll go away. Okay, well what's happened probably is this. So you see the sun shining on the earth. Okay, basically this could be a farmer that's plowing, basically have a freshly plowed little plot here compared to kind of around it. One of the things about farmers having, or I shouldn't say farmers, but one of the things about like the land having different colors even, okay, let alone kind of different textures is, I think we talked about this before, if you wear a black t-shirt on a hot sunny day, you're going to get, basically it's going to absorb all the colors that the sun is sending you. If you wear a white t-shirt on a hot sunny day, basically that white is going to reflect all of the light back. So picture this as something dark. It absorbs the energy. It makes it nice and toasty. Okay, and then basically, have you ever heard, or actually if you have a house that's 2 stories, okay, and you're wondering which story is going to be, you know, your bottom floor or your top floor, which one's going to be warmer? It's probably your top floor. It's all drafts aside, because actually warm air does rise, and that's actually what's happening here. It's called convection. So the chunk of air will actually rise, and this is a good example. Actually, all the examples are. I'm looking for my pen. It will show up. If you can get it to rise, oh, thank you. If you can get something to rise and expand kind of all at once, this is actually why clouds mostly have flat bottoms. Kind of all at once, you're going to reach a temperature where condensation is going to occur. So actually, this is a good example of having that, what we call the lifting condensation level, or LCL. I think it might be the last thing on there. It's the elevation that you need to lift a chunk of air up so it gets large enough so it cools down for condensation to begin. Reach 100% relative humidity. So then the last one, okay, to me this last one probably doesn't happen much around here. But actually, as air blows from something like the ocean or the Gulf, okay, onto rough land, like the peninsula of Florida, okay, it's kind of like if you were to take a hockey puck and you were to have the nice ice, and then you would have the sand over there, okay? Basically, you take the hockey puck and it goes on, glides on your sand, glides on your ice and it hits the sand, it kind of slows down, kind of bunches up, and that's what happens there in Florida. Okay, it's called convergence lifting. Okay, so the LCL, the lifting condensation level, that actually is why mostly clouds have flat bottoms. Okay, it's like an elevation. Now, when I talk about the 10 different types of clouds, by just like looking at the different clouds, I'll kind of tell you what characteristics you're looking at for in order to give a cloud a classification. It's possible that you can have kind of multiple types of clouds, multiple types of elevations of lifting condensation levels, but okay. So precipitation is another thing that we're worried about when we get up in the morning. Is it going to rain? Is it going to snow? Is it going to sleet? Okay. Precipitation by definition is when water is falling from the Earth's atmosphere onto the Earth itself. For that reason, as I understand it, frost is not precipitation, dew is not precipitation. It's actually taking water vapor from the atmosphere, but it doesn't fall. So I guess I'm okay with that. So I want to start with cold clouds, and then we'll end with warm clouds, okay? But in cold clouds, now what do I mean by cold? Well, probably cooler than the freezing point temperature of water, which you guys would tell me in Fahrenheit is 32 degrees Fahrenheit. So 32 degrees Fahrenheit, colder than that. So what's going to happen up in the cloud is you're not going to be this misty thing, okay? Actually, it's going to freeze and going to carefully freeze into these cool snowflakes, snow crystals, okay, at higher elevations. As far as I know, I've never seen somebody like actually take liquid water down on Earth and have some sort of chamber. I guess you could, and make your own snowflakes. Leave that up to the good Lord to do. Okay. But snowflakes form at temperatures that, in clouds that are cooler than the freezing point temperature. They call that the Bergeron process, so that probably, I like that word, probably end up on your next unit exam. All right. So, but it's quite possible that what starts out as snow actually is going to fall as not snow. That should bring a happy smile to your face. These spring showers we get, and maybe even some summer showers, actually start out as snow. Okay, but as they fall, one of the things you might already know is the temperature in this layer anyway of the atmosphere where most of the weather is, the temperature actually gets warmer as it gets closer to the Earth. Okay, so the stuff melts. That's it. And we get rain. Okay, so I have a few examples here. Notice it's even showing that it falls. Anytime you see blue on these figures, blue means that it is actually colder than freezing, and pink means that it's warmer than freezing. So you kind of see that transition zone. Okay, so that's rain, okay? And of course we can get snow. All you need to do to get snow from a cloud that creates snow is to make sure it's colder than 32 degrees Fahrenheit when it hits the ground. Well, there's a couple of other forms of precipitation that actually go together that I want to talk about. Notice we have blue, pink, blue. Blue means water freezes. Pink means it is a liquid, and blue means it freezes again. So these two, like I said, actually go together. So we have this scenario and this scenario. This scenario is called sleet. These actually usually kind of look like little pellets. Not to be confused with hail, because actually hail, this is not hail. We'll talk more about hail when we talk about thunderstorms. It's sleet. The difference between sleet and when it says glaze, I think I want to put equals freezing rain. I hate, and so do most people, unless I'm staying home for the day, and everybody I love is staying home for the day, I hate freezing rain. It is terrible. It is awful. The thing with freezing rain is, can you see where the kind of the cool layer is not very deep. This, where it's going to refreeze, okay, It's just pretty what we call shallow. And the meteorologists like to talk about shallow, deep, okay, shallow. Okay, it doesn't have time to pelletize. Pelletalize. Sleet is more like pellets, I think. Sleet I'm okay with. Freezing rain, I am frankly not. Okay. So this hole where you have blue, pink, and then blue, blue, pink, and then blue, where basically you have water freezing, okay, water melting, and then water freezing again, that actually is what we call a temperature inversion. The word inversion kind of seems like it shouldn't be that way, and that's true. A temperature inversion is kind of an anomaly. It's kind of weird. One way to think of it is basically you have kind of cool air kind of inserted itself where it shouldn't be, is what I think. Either that or warm air kind of inserted itself in between two pockets of cold. So somewhere something has gone amiss, temperature inversions. Okay, well, let me see. I have this and then clouds. Now let's hold off warm clouds and then cloud types until Wednesday. So we'll I like the idea of having the cold clouds separated from the warm clouds. Very good. And I don't have any assignment for you.